In this video, we're going to look at the chair conformations for six-membered rings and how to draw these chair conformations and manipulate them in two dimensions. Remember that cyclohexanes and other six-membered rings can adopt this very special chair conformation. A chair conformation is just a very stable conformation for any six-atom ring. It's stable because it has almost no angle strain, it has no torsional strain, it has only a very slight amount of steric strain from the gauge interactions from the actual carbons in the ring. If you look carefully at a model of a chair conformation, you'll see that some of the groups attached to the carbons of the ring are kind of pointing straight up and down, and some other ones are kind of pointing outward at funny angles. The groups pointing straight up and down, we refer to those as axial positions. Here I have them in green. The ones sticking out of the ring at sort of slight angles are referred to as equatorial groups or equatorial positions. Here I've got them colored in red. If you look closely, you might notice a few more things. Look at any given carbon. Let's look at, say, this leftmost carbon. You can see that that carbon has one group pointing up, in this case, that axial hydrogen, the green, right? But it also has a group pointing down, or at least downward. We have that red hydrogen pointing slightly down, and that's equatorial. This is going to be true for every carbon in that six-membered chair conformation. Every carbon is going to have one axial group and one equatorial group. It's also going to have one group pointing upward and one group pointing downward. Now, using 3D models is very useful, but we need to transition into some two-dimensional drawings of these chair conformations. So here I'm going to show you how to draw chair conformations. Start off by drawing two parallel lines, roughly at maybe a 30-degree angle, that are offset from one another. So here you see these two lines. They are offset so that one kind of ends about midway through the other line. So the top one and then the bottom one starts way over to the left so that it ends about halfway through the top line. We're then going to connect the closest ends, the leftmost ends and the rightmost ends, using little V's. The ends that are kind of on the downside, we're going to connect with a V that is pointing up and away from the lines. The ends that are kind of on the high side, the upper side, we're going to connect those with a V pointing downwards and again away from those lines. If you do it right, it kind of looks like the logo from a popular beer company. So just after that, you can see we've created a six-membered ring, and you can kind of see the puckering action of that chair shape. Now we need to add all of the substituents, the groups attached to those six carbons. The easiest way to do this is to start with the axial groups, because we know the angle, right? Axial groups are either pointing straight up or straight down. So this is really just a special kind of skeletal structure, and remember that in a skeletal structure, the intersection of any two lines represents a carbon. So every carbon atom in this ring, where the two lines intersect and have an upward pointing angle, you're going to draw your axial substituent pointing upward. So if you look, we actually have three carbon atoms that are formed by two lines intersecting, kind of pointing upward. So we're going to have three axial hydrogens in this case, pointing up. Here I've got them drawn in green. Now, everywhere you have a carbon drawn out from the intersection of two lines pointing downward, then the axial position is going to be drawn going straight down. Again, you can see I have three of those, right? Three axial hydrogens drawn straight down in green. Now, once the axial groups are drawn in, it makes adding the equatorial groups a lot easier. We just have to remember a few things we mentioned before, that every carbon on a chair conformation has an axial group and an equatorial group, and every carbon on the chair conformation will have an upward pointing group and a downward pointing group. So look at the leftmost carbon in this drawing. Right now it has one group attached to it, and it's an axial group pointing straight up. Think about what that means. Because this group is axial, the remaining group must be equatorial. The group that's there is also pointing up. And that means that the other group attached to this carbon must be pointing downward. That means that the other hydrogen attached to this leftmost carbon must be pointing downward and must be equatorial. Now, to get the angle right, we simply draw this bond so that it is parallel to a bond two lines removed from what we're drawing. So if you think about it, I'm drawing a bond on this carbon. Go two bonds in any direction inside the ring, and you'll see two parallel lines. You want to draw this new bond parallel to that. And always draw your equatorial groups pointing away from the ring. Now all you have to do is repeat it for every carbon on the ring. If we move clockwise from that leftmost carbon, look at the next one. We have a hydrogen that is axial pointing down, and that means that the other group must be equatorial and pointing upward. If you look, we want to draw it parallel to two lines over, and that means that this bond, for example, is what we want to draw it parallel to. And again, remember to draw it pointing away from the ring. So once you've done this for all 6 carbons, you get a drawing that looks like this. And you can see every carbon has an axial group in green and an equatorial group in red, and that every carbon has one group pointing upwards and one group pointing downwards. Now, as it turns out, every 6-membered ring actually has 2 possible chair conformations. It's kind of like when we looked at ethane and other molecules like that, where you would have 3 possible staggered conformations, right? It's kind of the same idea here. When a 6-membered ring changes from one chair conformation into the other, it's called conformational inversion, or a chair flip is kind of a slang way of referring to it. So if we look at the animation here, in the initial model, we see that all the axial groups are in green and all the equatorial groups are in red. When the inversion occurs, you can see that it inverts, right? All of the green groups are now equatorial and all the red groups are now axial. Now, without those colors there, you really wouldn't be able to tell the difference. In fact, for cyclohexane itself, there's really no energy difference between these two. They're indistinguishable from one another. I think the easiest way to envision what's happening during a conformational inversion of a cyclohexane is to think about what it is. It's a chair, right? And remember, it's supposed to look like a lounge chair, where you have sort of the seat that's flat, and then you have a headrest, and then opposing that you have the footrest. What we're doing in a conformational inversion is we're taking the footrest and lifting it up so that your knees are in your face into what's called a boat conformation, where we actually have 2 carbons now pointing upward. Then what we're going to do is we're going to take the original headrest and we're going to push it down into a new footrest. And you get a new chair when you do that. And that's really all that's happening when we do a conformational inversion of a 6-membered ring. Simply take any carbon that's sort of pointing upward, shove it down into a sort of footrest, and then take the opposing carbon, the one that's furthest away, and push it in the opposite direction to make a new headrest. Now, these chair flips are pretty straightforward when you're working with models. To do it in 2 dimensions, to draw these out, is a little bit more work. So let's say that this chair on the left is my original chair and I want to draw the inversion of that. Remember how you draw these chairs to begin with. You start with 2 parallel lines that are kind of offset from one another and then kind of connect them with these V's, right? We're going to do the exact same thing, except we have to start with 2 parallel lines of opposite slope. So in the left chair, I started off with my 2 parallel lines having positive angled slope. That means that in the chair inversion, I need to start with my parallel lines aligned with a negative slope. Again, offset, so that one starts at about halfway through the length of the other. From there, we simply finish off the drawing. We connect the higher ends with a V pointing downward and outward. We connect the lower ends with a V pointing upward and outward. And then we go ahead and add the axial positions straight up or straight down, and then the equatorial after that. So it's really the same process as drawing the original chair. We just have to start with our parallel lines having an opposite slope. Now, to make sure that all the groups are attached to the right carbons and in the right locations, it's important to look at these drawings from the right perspective. I like to read chair conformations kind of going left to right. In other words, if you look at these 2 conformations of cyclohexane, the leftmost carbon in each drawing is the same carbon. And it's very tempting to think that the leftmost carbon on the left drawing is in fact this carbon on the right drawing, but it's not, right? It looks like spatially that makes sense, but it's actually not what happened. And if you think about how this chair inversion occurs, where we take a footrest and push it up, and we take a headrest and push it down, you might be able to see that that's not right. The leftmost carbon on the left conformation is also the leftmost carbon on the right conformation. That, of course, means that the rightmost carbon is also the rightmost carbon on the second drawing as well. So starting from that leftmost carbon in the original drawing, you can see that we have an upward pointing green axial hydrogen. Look at the leftmost carbon in the right structure. You see how it now has an upward pointing green equatorial hydrogen. This is pretty much how it works. When you do a conformational inversion of a 6-membered ring, Whatever was up stays up. So see how the green hydrogen is pointing up in both conformations? What's down stays down. See how the red hydrogen on the left structure is pointing downward, and the red hydrogen, again, on that leftmost carbon of the right structure is pointing downward. But what was equatorial becomes axial, and what was axial becomes equatorial. So again, look at the left carbon, the leftmost carbon on that left structure. The green hydrogen is axial, and the red hydrogen is equatorial. But when we do the inversion, again, looking at that leftmost carbon, it's now the green hydrogen that's equatorial and the red hydrogen that is axial. Let's take a look at another example. Here I've got a disubstituted cyclohexane. This is actually 1,3-dimethyl cyclohexane. If you look at the leftmost carbon in the original drawing, it just has hydrogens on it, and without color, you really can't tell the difference. So you can make quick work of it. It's the leftmost carbon on the left structure, and it's got 2 hydrogens on it. Just draw 2 hydrogens on the leftmost carbon in the right structure. Now, to get all the other groups in the right places, what we're going to do is we're going to work our way around clockwise on both drawings. If we go clockwise on the left structure, the next carbon going clockwise has a methyl group upward and equatorial, and a hydrogen downward and axial. Now, find that carbon on the second conformation. It would be going clockwise from the leftmost carbon, and that's here. So what we had was a methyl group that was upward and equatorial. Well, remember, up stays up, but equatorial becomes axial. And sure enough, look at the axial position on this drawing at this site. It's going up. So we draw our methyl group in the upward axial position. The hydrogen atom on the original conformation was downward and axial, which means it should now still be downward, but flip to equatorial. And again, if you find that carbon in the second conformational drawing, you can see that the downward position is in fact equatorial. So we have a downward equatorial hydrogen. From there, we just continue to work our way around clockwise on both drawings. When we go clockwise on the left original drawing, we see, again, we have 2 hydrogens, so it doesn't matter, you can't tell the difference. So find that same carbon on the new drawing and simply draw in 2 hydrogens. Going clockwise again on the original drawing, we're actually at the rightmost carbon in that drawing now, and you can see that it has a methyl group up equatorial and a hydrogen down axial. So when we go to the new drawing, find the rightmost carbon there. We're going to have a methyl group now pointing up and axial because it was up and equatorial. And we're going to have a hydrogen pointing down and equatorial because in the original drawing it was down and axial. Going clockwise again, well, we've just got 2 hydrogens here. So again, go back to the new drawing, go clockwise from where we just were and just draw in 2 hydrogens because you can't tell the difference between them. And then going back to the original drawing, again going clockwise, yeah, just 2 hydrogens again. So go clockwise from where you left off on the new drawing, and then just add your 2 hydrogens. And that's how you draw out a conformational inversion. When we start looking at substituted 6-membered rings and the chair conformations of those, there can in fact be differences in energy. Think about it, cyclohexane has 2 chair conformations, but without any coloring of the actual substituents, you can't tell one from the other. They're indistinguishable, and they have the same energy. But that 1,3-dimethyl cyclohexane we just looked at, the 2 chair conformations for that actually looked different. In one chair conformation, both of those methyl groups were equatorial, and in the other, those 2 methyl groups were both axial, and you can definitely tell the difference in their shapes. It turns out that when larger groups occupy axial positions, they can introduce a new form of strain called 1,3-diaxial strain. And 1,3-diaxial strain is really just a special form of steric strain. Remember, that's just when big groups kind of get in each other's way. If you look at the diaxial conformation of this disubstituted ring, you can see that the methyl groups in the axial positions kind of get really close together in space. Whereas in the equatorial positions, right, the diequatorial conformation, those 2 methyl groups are actually pointing kind of in opposite directions. They're very far away from each other. And that means that the diequatorial conformation is going to be more stable than the diaxial because it has less of that 1,3-diaxial strain energy. And this is generally going to be true. Overall, when you have substituents on a 6-membered ring, the more stable conformation will be the one that has more of the larger groups in equatorial positions because it minimizes the chances for those 1,3-diaxial strains.